Right, and I will give you one of the earlier theorems of Ratner on the topic. I will talk about Ratner's vector theorem today, and we will use the language that we have set up so far, and it will simplify the proof a lot, but there's a crucial step that I can do in this case, which I can keep entropy free. So let me tell you the statement. Let x1 be g mod gamma 1, x2 equals g mod gamma 2. Gamma 1 and gamma 2 are lattices in G. G is SL2R. And let phi from x1 to x2 be a vector map for the horocyclic flow. What does that mean? It means by definition very little. I mean, the requirement to be a vector map is for many dynamical systems a very weak assumption. So it's a measurable map that's defined almost everywhere, and it is behaving well under the flow that we have and we currently discuss. So measurable defined almost everywhere, and phi of x one minus s1 is equal to phi of x 1 minus s1, because that's our flow that we are studying. And we need to have that property for almost every x. That's the assumption. And the conclusion is an amazingly strong one, namely it is algebraic. Phi of x times g is equal to, I would like to say, phi of x g. But that's not quite true, because if I have a map that satisfies this, and I then apply an element from the flow, from the U flow, from our unipotent flow to the map phi. So I first apply the map phi, and then I apply one of these elements. Then I don't change this equation, because the U flow will just commute with phi and I can pull it in, but it doesn't commute with G. So the statement is that this is true up to another U S0. Doesn't matter. Up to conjugation by another U S0. That's the statement. And once you have this equation, you can obtain further information. The gamma 2 or gamma 1 conjugated by some G naught is contained in gamma 2. So the lattices are not that different. That's a conclusion of the theorem. So not only is the map always very nice, the lattices need to be very closely related, or otherwise you can't have such a vector map. Okay. So what does it have to do with the measure classification, which we are trying to discuss in this lecture series? That's a standard procedure. Whenever you have a map, say a vector map or an isomorphism, you can of course consider instead of the map, the graph of the map.
What is G naught?
Some G naught in G. Some. Plus minus 1, it's the image of the identity. I mean, it's almost everywhere, so It's determined by phi in some way. And after you have made, this statement is almost everywhere, but then once it's almost everywhere, you can say it's true everywhere. And once it's true everywhere, you can say, you can ask what's the image of the identity coset. And the image of the identity coset is some other point in the other space, and there's some other G appearing, and this G naught is related then to this other G. So if you have a vector map, you can instead consider the graph, and you can instead consider the joining on the graph. And let me write mu on graph, and that's very easy to define. You define the measure of a subset B. B is now a subset of x1 cross x2. The measure of B is the set measure, the H measure of the set of all x in x1, for which x1 cross phi of x1, which is in x2, belongs to B. That's the definition of an invariant and ergodic probability measure. On x1 cross x2, invariant and ergodic under what? Under the flow, but which flow? It's the diagonal horocycle flow. Of course, that looks like a contradiction, but I have a product space, right? So let me write U maybe for this group. U is the group 1 minus S, or 1S1 cross 1S1 S and R.
So you make small x1 and big x1 and m1?
What? There's no, yeah, sure.
So what looks like a contradiction?
Hmm?
What looks like a contradiction?
Don't remember. Wasn't very important.
Diagonal unipotent flows.
Ah, yeah, diagonal is not usually unipotent, but it's diagonal across x1 cross x2, and it's unipotent because it's unipotent. And what's worth pointing out is that it's not a horosphere. When this was a horosphere, it was the horocycle. This is a horocycle, but this diagonal horocycle is not a horosphere. So it doesn't fit into the previous discussion, the old discussion of using the mixing argument to classify invariant measures. Now, if you can classify this invariant and ergodic probability measure, or let's phrase it differently, if you already know Ratner's measure classification, then you realize that this nice joining must be a H measure of some orbit, and because this joining has another property, namely that the measure of B1 cross x2 is always m of mx1 of B1. Because of that, this algebraic group that appears needs to be a diagonal copy of SL2. And you also have this in the second coordinate, and because of that it's a diagonal copy of SL2. And if you know all of that already, then this is a very easy corollary. So that's not what I want to explain. I want to explain how to get the conclusion that this measure is algebraic. And then this is what we get out of it. Any questions? Many of the steps that I want to do, that I will have to do, are similar for a general joinings case and also for a general case of invariant measures under this U and measures that live on G cross G mod sum gamma, irreducible or reducible. So many of the steps are much more general, but at some point it will help me to have this factor in the background because it simplifies some of the discussion. Okay. Now of course we again look at the stabilizer. We want to show that mu is supported on a single orbit of the stabilizer. As defined previously, just the elements of all group elements in G cross G. Will be slightly annoying. That's what we want to show. Again, we can use generic points. Our unipotent, this is our unipotent flow. It's invariant and ergodic by assumption for this measure or by construction for this measure. So there are generic points and there are large sets of uniformly generic points as always. So we can have points y, which is a point y1, y2, which is an x times a g, which is an x1, x2 times an g1, g2. Right? Every letter in the previous discussion now is 2 coordinates. And if G is in the normalizer of the group U and X and Y are both generic, then we get that G is in the normalizer of U, in the stabilizer of the measure. That's the easy lemma where you just need to look at one orbit and look at the other orbit a bit shorter depending on how much the G in the normalizer shortens orbits or lengthens orbits, and both things equidistribute and we preserve the measure. So that's as before. Now, because we know that our measure projects, we know that we aren't always in that situation. Because if you always, let me just write down what the normalizer looks like. The normalizer in G, which is G cross G really, of the group U, which is the diagonal horocycle, this normalizer, you think about it for a while, not too long, looks like this. Here it doesn't really matter. S1, S2, everything up here commutes with your horocycle, even the diagonal horocycle, so there's no constraint. Now, if you have a diagonal element that used to normalize the flow, and it still normalizes flow, but only the diagonal normalizes the flow. Not the contradiction. That's the normalizer of our diagonal unipotent. But of course, the measure projects to the H measure on x1, our domain space. And because of that, we need to be able to find generic points that are not just in the normalizer. So this case is in the discussion of vectors not very interesting. We are sure to find, I mean, it's interesting if we are lucky to achieve that situation. If we are lucky and we get the situation, fine, good, then we have found something. But we have to consider the other case anyhow, and we know that the other case has to happen also, because this is too special in our situation. So let's just say, suppose now G is not in the normalizer of U. Then we want to play the other game, the Xi argument, right? We start the orbit, we had our space, and then we had one orbit for x, which equidistributes in the space and becomes, and looks after a while very complicated. And then we had a second orbit, which is traveling very closely to the original orbit, because we start off very close to the original. And then the first thing that happens after some time is they may start, now I don't know any longer, because my space is much bigger, but they may do that. They may diverge first in the direction that I understand, in the diagonal horizontal direction. If they do that, then I just keep going for longer, as in the previous discussion, and wait until I see divergence that is really transverse to the flow direction. That's what I want to do. So I have to remind you of the calculation we did yesterday. So we conjugate matrices, right? But we use different times for the point x and for the point y. And we have now this displacement which has two copies. So I need to amplify this discussion here by putting not indices along a sequence, but indices in the sense of this index. I have to put, so G1 is an A1, B1, C1, D1, the G2 is an A2, B2, C2, B2. And so I have to put this I equals 1, 2 at every letter that I have here. Right?
The Sx and Sy are the same for I equals 1.
Say it again?
The Sx and Sy are the same.
Yes. So I use the diagonal unipotent, which means that the S is an Sx and an Sy, but not an Sx1 and Sx2. That I don't have, because it's the diagonal unipotent that I'm using. Which means I have only two variables, and I want only one equation to link the two. Right? So let me schematically give you this conjugation really in the product. So we have our 1 Sy, y1, 1 Sy, 1, and then we have this G1, G2, which is A1, B1, C1, D1, etc., etc. And then we have this 1 Sx with a minus 1, 1 minus Sx, 1. And we have this calculation twice, where we have here the C1, and here the C2, and then maybe one term, maybe I write down this term here, D minus D1 minus C1 S y Sx, damn it. And here D2 minus C2 Sx also. And then I have here a quadratic term, which is the most complicated term, and here I have a quadratic term, and here I have some other linear term. This other linear term is not so interesting because, first of all, later it will be determined. Once the C is 0, I know that the determinant is always 1, so this corner is not relevant. What is relevant are these two quadratics, but as long as I'm ensuring that one of these quadratics goes to 0, I know that I'm transverse to the diagonal horocycle that I'm working with. Because the diagonal horocycle is identity here some entry, identity, and the same entry. If one of the two entries is 0, then I'm happy. So I just use this equation that I indicated last time on one of the two, in one of the two corners. Say for the first group, I use this formula. So we use Sy equals d minus d1 minus c1 sx a1 sx. I use this formula, which means by this formula that I put here in the limit 0, I put here the value b really, b1 really, and that goes to 0. So by choice I made that entry b1 plus 0, and that means here I have still a quadratic term. Well, now a rational function also, but okay. Now I want to speed up. I want to use Zeitraffer, for time lapse. I choose a time parameter so that this, if I don't do that, what would happen? This would converge to 1, 1, 0. This would converge to the identity. Sx would be equal to Sy. That doesn't bother me. That's okay if that happens. I'm happy with that happening. However, this function would converge to the identity. By which I mean not the identity map, I mean the identity polynomial that is equal to the identity all the time. The 1, 0, 0, 1, 1, 0, 0, 1 function as a time in the parameter Sx. That's the limit that I would get under which I can say that honestly that I'm invariant under, but it's not so relevant. So what I need to do is I need to speed it up. I need to make sure that this sequence of rational functions that I have here later, right, I need to have a sequence of such tuples of points, that this sequence converges to something interesting. You may be bothered a bit by that we are now renormalizing rational functions and they start to become more and more complicated. If you are bothered by that, just multiply this rational function with this denominator and make sure by your renormalization parameter that this polynomial map becomes interesting. And when this polynomial map becomes interesting, that's precisely when also the rational function became interesting. And then after having multiplied this rational with this polynomial, with this linear term here, I know uniform convergence on compact sets and all its derivatives, and that makes me very happy because I can now take the quotient again and get uniform convergence also for all the derivatives for these rational functions to some other rational function. So that's one possibility how to say rational doesn't really matter here. I just have one denominator that may also change, but I just multiply it.
Were you saying now that the space of rational function that you obtain is finite dimensional?
No, it's not really, because the denominators are changing, and when the denominators are changing, I'm not finite dimensional. But I have only one type of denominator. It's precisely this corner. This is my denominator. And I just multiply with this denominator here only once to make sure that I look at the polynomial instead. And then I speed up a polynomial, which gives me a polynomial, choose the converging subsequence, and then study the sequence of rational functions and realize that in particular one term that is not exploding is my d1 minus c1 sx. And now it's speeded up, so I have here a new variable. That this parameter gets changed by the speeding up. I don't know in which way. This squared. This is a polynomial that I know will converge. Which in particular means that this will go to 1 and this coefficient will go to some coefficient, maybe 0. That's a possibility. Maybe not, but it doesn't go to infinity. That I'm sure of. which means that my pole doesn't go all the way to 0, it stays somewhere bounded. Maybe the pole goes to infinity, that's okay, that doesn't bother me. I didn't like it anyway, right? But it doesn't go all the way to 0 along the sequence. So I'm not, it works out nicely. I'm not really bothered by the fact that it's rational functions. I can get rid of the denominators because it's one simple type of denominator, and then choose my converging subsequence and choose my renormalization and my converging subsequence. Does that sound convincing? Are there any questions to this step? I
What's
don't
the
want to do
issue
it.
with one type of denominator? What would have happened if you had, I don't know, denominators, varying denominators?
Can you phrase it, I don't know, slightly more scientifically? I mean, do you have a projection on some finite dimensional space here?
Let me just write down the polynomial that I want to study. So let me introduce a name for this. F of Sx. We already used this formula in here, which means that f of Sx is rational, right? And now let me just define a new thing, which I think is slightly nicer because it stays in a finite dimensional space, which is I take my f of Sx and multiply it with my denominator d1 minus c1 Sx. That's now a polynomial. And just for safety, let's add the linear term that I'm using also to the expression. Now I have a polynomial in a finite dimensional vector space. And if I change my time window, then all the linear terms get amplified a particular amount, and the quadratic terms get amplified by the square of that amount, and so on. So amplified precisely by the right amount. You could write down a formula involving many terms involving all of these coefficients with index 1 and index 2, and then a maximum, or maybe a minimum depending on how you write it. And this is how you would amplify it, but it doesn't matter. If we don't want to know, if we don't want to write down this formula, it's too annoying. There is a time parameter so that this polynomial, maybe minus the identity, because we don't like the constant value, then has norm 1. Good. So subtract the constant term from this whole expression, and that's the thing that I want to have norm 1. So that means one of the linear terms has absolute value 1 about, or one of the quadratic terms has absolute value about 1, or one of the cubic terms has absolute values about 1. One of the interesting non-constant coefficients of this polynomial has absolute value 1. In particular, this thing also converges along some subsequence, which is my denominator, and is very easy. Now I divide my uniformly converging sequence of polynomials, this one, by my denominator, which is also uniformly converging, and in some intervals staying away from 0, so I can divide, it doesn't matter. It's easy. So what I get is that f of t n tau, that's fn of t n tau, converges uniformly on some compact subset to some f of tau. And then I apply the previous argument to where I use this uniform convergence together with the definition of uniformly generic to make the claim that this preserves for values tau within this compact set.
So when you take the limit of the amplified f twiddle,
Yeah.
how do you know that the significant term is not there exactly and
That's okay. If you look closely, it's fine. It's just fine. If this is the term that is significant, I'm happy. It's a non-trivial entry precisely in my matrix. I'm perfectly happy with that. So, yeah, you don't want to just multiply your rational function with some denominator that comes out of the blue, and then also quite comma this denominator, and then normalize according to this. That would be stupid. But what we normalize with is actually appearing without the denominator, right there in our object. And if that's interesting, and everything else goes to zero identity or whatever, that's fine. I'm happy with that. Okay. So, we get a rational function and the statement that the measure is normalized, preserved by values, small values of this rational function. So now the question is, how does this rational function really look like? Now we could of course do this calculation and really figure out the precise conditions on this renormalization parameter and then realize what all has to go to zero. That would be too annoying, even in this case, and would be even more annoying in other cases. So let me give you an important feature of this rational function, which is what we want to know. Lemma. F of tau has values in the normalizer of U. And the proof is easy. You look at the F easy but might be confusing. So what I want to do is I want to take f of tau and add here a u1. That's the u that actually appears in my definition of my f. So f tau u1 is of course the limit as n goes to infinity of fn tau u1. I mean that's nothing, right? But now I know what the definition of fn tau was. I know this is defined in terms of I need to take my g1, g2, then my u for the parameter tn tau, and here I will need to take some other u. There is some other parameter that is precisely our function that I killed. I mean, that's precisely how we defined sy. Sy is on the left as I've set it up, and sx is on the right. This is our sx, the independent variable, and here I have some depending thing. Whatever. And this is multiplied by u of 1. So let me do this differently. Let me put this u of 1 in here. Which then it means that it's tau plus 1 over tn. But we always think of 2 points that move closer and closer together, which means that the speeding up parameter Tn goes to infinity, so this thing here goes to 0. I can make this whole expression look precisely like Fn of tau plus 1 over Tn. Because the Fn tau plus 1 over Tn has this part is identical in the definition for Fn tau plus 1 over Tn. But this part of the question mark, which I didn't write down, is different. So this is limit n goes to infinity, u question mark prime, g1, no, let me just write it, Fn tau plus 1 over Tn. Right? But I have uniform convergence. And the Tn, 1 over Tn goes to 0. So it doesn't matter in the sequence. So this question mark is a difference of 2 question marks.
That's the correction that you need in order.
Yeah, to make it match precisely. But I don't want to write it down. And now that 1 over Tn goes to 0, the Fn converges uniformly on the compact subset where I'm currently working with to my function f. So I realize that this u question mark prime must have a limit because this has a limit, and I started with something that converged, so this converges to something. But if it converges to something, it has to converge to an element of u, because u is closed. So I get u of question mark double prime, which now is not depending on n, comma f of tau. That formula, if you think about it, and maybe slightly generalized with an S here, is precisely the statement. Okay? Now it helps a bit because the normalizer we just calculated. And so we don't have to calculate the limit, we don't need to know the limit. As long as you know that the limit is interesting, which we ensured, and we have a description, a good description of the normalizer, we can keep working. Because we're not really interested in the rational function after all, we're just interested in getting new invariants. When did I start? That's bad. Okay. Now, so far I haven't used that my measure comes from a factor map or from a map. But now I can start making use of that.
Big the blind spot.
Yeah, that's true. Case 1.
Change the path.
I already did. Case 0 is not interesting. Maybe f of tau takes on values in this part of the normalizer. Now, f of tau has here zeros. We know that by construction. Maybe f of tau takes on values in here. No, it doesn't, because that would mean that our graph, our measure on the graph is invariant under a vertical direction. Graphs usually are not invariant under vertical directions. So that's not happening. Case 1, which is the remaining case, it's equal to some alpha inverse cos alpha inverse. That's the only normalizer that we have. cross something here, S2. But if that's the case, we just conjugate. If the S2 is not 0, we just conjugate the whole picture with the correct thing on the non-diagonal unipod. And we conjugate with something like that. And with the correct choice of S prime, we can get rid of this S2. Because the alpha is not equal to 1 now. It's close to 1 because you have a continuous rational map, so you can make the alpha close to 1 if you want to. But by conjugating the measure and hence also the vector map with something like this, I mentioned that possibility also in the beginning, you can get rid of that possibility and you simplify life a bit. So we have shown invariance under an element of the diagonal subgroup. Non-trivial element of the diagonal subgroup. So you could continue in two ways. First way to continue, which is
there's no
in some
case
sense.
2, right? It's just your case 0 and 1 and that's it.
Yes, that's it. And 0 didn't appear. Yes. The first case is actually the second case, let me say it in this order. With entropy. You could use entropy now to keep going, and let me not do it now. Maybe tomorrow if we feel up to it. I mean, if we, depends on how the time proceeds. Maybe we just do this case or we do some other case with entropy. But let me not do it. The first way to continue is an argument by Marina Ratner. The second way is the Margulis-Tomanov approach to keep going. And that is now, that I want to phrase now special to the situation of a vector map. So now I change discussion. I don't talk about invariant measures any longer. If you force me, I would go the second way to do that. But I talk about the vector map. What do we have? We have shown that phi of x alpha alpha inverse is equal to phi of x alpha alpha inverse for almost every x. That's what we have shown so far, because when the measure on the graph is invariant under the diagonal flow, then the graph is almost everywhere invariant under the diagonal flow, which means that the vector map has this property. So of course it also had this property that when we had an S here, we could also pull it out. That's what we started with, and we upgraded this to the same behavior for 2/3 of the group. What is missing is this corner, right? We want also phi of x 1t1 equals phi of x 1t1. Then for almost every x. If we have that also, we have all three directions, and we can generate the whole group and have the statement that I wanted.
Earlier there was some...
The conjugation disappeared because I conjugated at that stage. I killed that by a conjugation, and that's precisely the conjugation that was mentioned in the theorem. It's just to simplify, otherwise I have to carry it around, it's annoying. Okay? What's next? Well, we will apply almost continuity of the vector map. So we take a Lucent set, let K subset x1, that's my first quotient where phi is defined, satisfy mx1 of k bigger than 1 minus epsilon, and phi restricted to k is uniformly continuous, of course, because I've also chosen it compact. Right, and let's make this an eta, because then I have epsilon delta for the uniform continuum. So epsilon is small, smaller than injectivity radius divided by 100, and delta is accordingly.
Manfred, would
Yeah.
you assume at this point that this goes, you have the invariance by all the diagonal subgroup, or just?
It doesn't matter, I only need the discrete one, that's okay. Once I get the opposite unipotent, I'm happy, right, to degenerate. But actually I have everything. I actually have everything because I have a continuous thing.
If you have the diagonal, the all upper triangular group, you can dualize and look at the map from G mod P to G mod gamma.
Let me do it Ratner way, because that's what I... Maybe, yeah, could be that. I'm sure that there are other ways too. But okay. Now let y be let choose y different from x in the direction that we're interested in. For t smaller than the delta, much smaller than the delta later on. That means that phi of y is close to phi of x. So it's phi of x times an ABCD. Now the ABCD is happening only in the second coordinate, so I could simplify notation from the previous nightmare. But I don't know this ABCD, that's the annoying thing. I want to show that this ABCD is 1, 0, t, 1.
If both x and y are inside k or something?
Yes. Thank you for paying attention. Now, I want to apply, the thing that I understand is the unipotent, right? So let me apply to x the unipotent, or yeah, to y. If I apply to phi of y the unipotent. Let me write it down. I flow by US. There are too many unipotents. I flow by this one. I flow the y in the horizontal direction that I understand. Now, we did this before. I can understand how the displacement behaves in terms of conjugation. And on the domain, my displacement is precisely of that form. I do this calculation currently in the domain, in x1. And I see a quadratic. It's precisely this quadratic expression where I now kill the indices in the s parameter. That's the thing that I see, except much more special than that. Namely, I have here 1, 0, t, 1. So it's a very easy thing, and it's a quadratic.
The signs of somehow the s's are somehow random.
Better. Good, thank you. It is a quadratic, and I know how big the t is. I have chosen the t, after all. So I can calculate the time when this quadratic is still small, which is delta small for all s with absolute value s less than delta, maybe I need another constant or something, delta divided by the square root of the parameter t. Because the t is the c here, and the c gets multiplied by s twice, it has an s squared there. And that's why I need to pay double attention to the parameter t. Do a small calculation, that's what you get. This is when it's still small. Maybe put here 1 over 10 to take care of the fact that I have 3 entries which are really changing and not just one entry that's changing, and to take care of the non-Archimedean property, the Archimedean property of the Archimedean world. Okay. That's the amount of time where I know that this quadratic stays small. Now suppose all the time I'm in the set of continuity. Then I would know something else for this. I need to do it in the right order. We define a set x1. x1 is the set of all x for which we are the orbit, the 1 star 1 orbit of x is 90% of the time in K. And let's say it's also in K. Then what we get from this discussion and the continuity discussion is that phi of y (1 minus S1) is epsilon grows to, because this quadratic, this displacement here, is delta small, right? So we put it into the uniform continuity of the function phi, and we just ignore it up to an epsilon and take the image of this guy. And we don't know that for all s, but for 90% of all s in a possibly large interval. If the parameter t is really small, then it's a large interval. But we have introduced this ABCD, and for this horocycle flow, this vector map is a vector map, and we can pull out the unipotent, right? So this is phi of y, which itself is phi of x ABCD, times 1 minus S1. And here we can also pull it out. This is phi of x 1 minus S1. This seems to say that the displacement between these 2 points, which I can calculate using this ABCD and conjugation, just like always, namely 1S1 ABCD 1 minus S1 is epsilon small for 90% of this interval. Okay.
Is it epsilon close to the identity?
The ABCD is close to the identity, yes. When it's epsilon close.
So the product is epsilon close to the identity and not epsilon small?
No.
Or
What I have is that this here is epsilon close to that here. And the displacement, I should say it more carefully, a displacement between these two is that here. And this seems to be the right displacement, but we don't know that at that point. We need to talk about that. That's the usual thing, right? What do I mean by a displacement, that displacement? If I have two nearby points, then there is a unique small displacement that moves from one to the other. That small displacement is unique, but there could be other group elements that move this point to the other point. And this here is possibly only a displacement between these 2 points. Let's ignore that for a minute. We have calculated what this is. This is this possibly quadratic, possibly linear expression. If this expression is really epsilon smaller 90% of this window, then how do polynomials look like? Polynomials look like this, right? Or they look like this if they are growing faster. But if they are 90% of the time small, then they are actually 100% of the time small. Now, we need to come back to the issue that this is maybe not the displacement, maybe it's a displacement. If this is only a displacement, maybe this thing which is a displacement, at the beginning it's the displacement, that's how I've chosen it. The ABCD is small. So let me draw the time window again. So that's the beginning. Here, that's the S equals 0 time. There I have my ABCD, my G equal ABCD. And that's really small, so let me draw it down here. That's my G equal ABCD. Now either this stays small all the time, and that's what I claimed, or it looks like this. Because it's a quadratic, or it's a linear term. If you fear about cancellation here, then okay, maybe there's no cancellation happening between a quadratic and a linear term, so it's always a quadratic thing. So this is my epsilon, and this is my injectivity radius. I insisted that my epsilon is much smaller than my injectivity radius. So for some amount of time, this conjugated displacement, which is for some other amount of time really that displacement, while I'm inside the injectivity radius, it's a displacement which is smaller than the injectivity radius, which means it's that displacement that I really want to consider, that only and smallest displacement. For some amount of time, here in this picture, for half of that window, that displacement that I have is epsilon small, and for the other half, it's not epsilon small. And then I have another window like that, where half of the time I would be epsilon small and half of the time I wouldn't. And then I have many such intervals, and together the claim is that I'm 90% of the time epsilon small. That can't happen if that's the picture. So the only other picture is that my displacement ABCD really gives rise to the displacement for 100% of the time. Okay, maybe at the end it's not quite true. So I get that this polynomial is small throughout this whole interval. But if this happens, I get to know something about ABCD. Because the C is the coefficient of the quadratic term. Here SC. If my quadratic polynomial is epsilon small for 100% of an, almost 100% of an interval, then this coefficient is must be appropriately small. What does appropriately small mean? The C is bounded. There's some constant, some 5, 10, whatever appearing. It doesn't really matter. Now the C is smaller than constant times the inverse of that squared. Is that the right thing? Yes, because this is the time parameter up to which I can go. And that parameter will be squared at the endpoint. And then it will be multiplied by C and is still bounded. So the C is less than absolute value t divided by delta. Let me just put the delta into the constant here. So I've shown that the C is not much bigger than the t. Okay, that looks like a rather weird conclusion after all this work. Let me add a bit more statements that are also coming out of this. The d minus a is not much bigger than the square root of absolute value of t, in the same sense. And the b I don't know much about. The b, well, it's less than epsilon. So I get these three inequalities that look rather annoyingly weak. Because what I want is this. And I guess I'm out of time, so let me finish this tomorrow and leave you in suspense. There's one more maximal ergodic theorem that we need. Okay, thank you. Are there any questions?
I have a comment.
Okay.
There are no questions. So, if you want to visit the German colony, then there's a very convenient way to do. The bus takes you to the hotel.